Hello and welcome back to Calculus 1, section 4.7, L'Hopital's rule. Disclaimer, it's not L'Hopital's rule, it's Bernoulli's rule. So L'Hopital was this really rich dude who loved to learn mathematics, and he was paying Bernoulli to be his tutor. It's a very interesting story. And then Bernoulli was one of the, well, Bernoulli brothers, more of them, amazing mathematicians, and Bernoulli was sending L'Hopital papers. So when you want to learn something, 200 years ago, you pay someone who knows, and then that person once a month or whatever, once in 2 months, sends you papers, and then you study those papers. Like, now, books, internet, and that stuff didn't exist at that time. So one of those papers that Bernoulli never published under his name contained this rule. And what happened was L'Hopital accumulated so much knowledge in calculus without inventing any of that, that he decided to make first ever calculus textbook. And this rule, that the world never seen before, for the first time appeared in the first ever written calculus textbook, and that textbook was written by L'Hopital. So people started calling it L'Hopital's rule, even though it was actually Bernoulli's invention, and so on. And we still today call it L'Hopital's rule to honor L'Hopital for writing first ever calculus textbook. So we know the truth, and we're just going to, turn the blind eye and say it's okay. Guy learned a lot, invested a lot of money, like all of you are doing, right? And then, there is something in history from L'Hopital. So, what is the L'Hopital's rule? L'Hopital's rule is the way to take the limits using derivatives. Now, you have to have a specific form for it to work, and we are going to study something that is called indeterminate form. When you remember that when you are solving limits, the most direct way and easiest way to solve the limit was to plug in a number. But in some cases, you would get 0 divided by 0, and I told you that that method failed. In some cases, for your horizontal asymptote problems, when you plug in numbers or infinities, you get infinity divided by infinity. So this rule is designed to deal with those types of situations. So what is L'Hopital's rule? The rule will compute limits containing indeterminate forms of, and here it is in blood, 0 divided by 0 or infinity divided by infinity. Right? So that's that. Just these two. And then we have modifications later. So the first part of the lecture is just learning how to deal with these two, which are the base cases. This is what's important. Now, the next part is to see 0 times infinity, infinity minus infinity, 0 raised to 0, 0 raised to infinity, and things like that. So that's coming later, and those are all modifications. If you are learning the rule is for these two only, and that's the end of the thing. So now, what does the rule say? The rule simply says that if we have indeterminate form 0 over 0, or infinity over infinity, then limit of f of x divided by g of x is going to be the limit equal by L'Hopital limit of f prime of x divided by g prime of x, as long as g prime is not 0, right? This is not a quotient rule, okay? It's not a quotient rule. It is the two separate derivatives. So technically it says that if you take the derivatives, the ratio within the limit doesn't change, even though functions did change. So the best and easiest example to learn this on would be the one that I asked you to memorize at one point in time. I asked you to memorize that the limit as x goes to 0 of sine x divided by x is equal to 1. I asked you to do that. But now you can actually compute this. So we are remembering from our chapter 2 that the fastest way to compute the limit is to just plug the numbers in. When I plug the number in, I get sine of 0, which is 0, divided by 0. I do have indeterminate form 0 over 0. Therefore, I can use L'Hopital's rule. L'Hopital's rule is used this way. You will put on the equal sign L apostrophe H, because what I'm going to write is not equal at all. That's why you must put L apostrophe H, because they're not equal. But their answers are, right? So you are creating a completely new problem, different problem, whose answer is the same as your original problem. So you have to be very careful about that. If you don't put the L apostrophe H up there, it's a wrong notation. It's -1 on the test, just like if you forget plus C for integrals, or you forget to put limit at all, and stuff like that, right? So it's extremely important. And now you take the derivative of sine x, which is cosine x, and you take the derivative of x, which is, the derivative of x is 1. Welcome. So the derivative of x is 1. So now you consider this problem. Now, in some cases, you will have to do L'Hopital's rule again. In this case, you cannot, because when you plug in 0, you do not get 0 over 0 or infinity over infinity. But we're lucky, because cosine of 0 is 1, 1 divided by 1 is 1, and we're done, right? So this is equal to 1 over 1 equals to 1. So what do we have? We have a problem, right, which we need to solve. We try to solve that problem by the most basic idea of solving limits, which is just plug in the number. If we get 0 divided by 0 or infinity divided by infinity, we are allowed to use L'Hopital's rule. L'Hopital's rule says, you copy the limit the same way, and then you take these derivatives separately. So no quotient rule. Derivative of sine x is a separate thing from the derivative of x. You take those derivatives separately, and what the rule is guaranteeing is that the answer for this problem, which you cannot do, and the answer for this problem that you can do is the same. So you must put this L apostrophe H over equal sign, because this and this is not the same. They are not the same, so you can't put equal in between them. But their answers are the same. And that's why we invent new notation and say the same answer will. So we are technically transforming a problem into a different, completely different problem that will have the same answer. Another example of this would be your asymptote examples from before. You remember how you had to divide by the highest power? It's time to start reviewing for the final, guys. We have less than a month. All right. So the limit as x goes to infinity of, let's say, 3x squared plus 5x minus 6 divided by x squared plus 4. I understand that by this time in this class you should be able to solve this problem in two different ways. One way would be to divide everywhere by x squared, which is what we learned in chapter 2. And dividing everywhere by x squared, everything dies except the front coefficients, and you get 3 over 1, and the answer is 3. The other way you learned even before, which is, oh, that's the concept for horizontal asymptote, and the horizontal asymptote on the same exponents is just coefficients, 3 over 1. So you already know two ways to solve this problem. But now, if I introduce the infinity, well, when I plug infinity everywhere, what I get is infinity divided by infinity. And that is indeterminate form. So if I have indeterminate form, I can use L'Hopital's rule. So this would be just another third way to solve this problem. Now, obviously, we're not going to use L'Hopital's rule to solve this, because you just look at it and you know. But I wanted one very simple example to have infinity divided by infinity. So this is infinity divided by infinity. And then by L'Hopital, we have that the limit of x goes to infinity is 6x plus 5 divided by 2x. Now, this is the time where you realize, wait, I can use L'Hopital again. Because this is still, when I plug in infinity trying to compute this, this is still infinity over infinity. So, boom. Another one. So that is the same as the limit. X goes to infinity. But now the derivative is what? 6 over 2. There's nowhere to plug this infinity anymore, and this is equal to 3, and you're done. So, you know, if we are not to cover all of the other external things, modifications, right, the lecture is over, technically, right? Because as soon as you spot 0 over 0 or infinity over infinity by trying to plug in and compute, right? Now, does it work for 0 divided by 7? No. Does it work 7 divided by 0? No. 7 divided by infinity? No, right? So it doesn't work for anything else other than strictly 0 divided by 0 and infinity divided by infinity. That's that. That's the limitation. So now you go to the homework portion of the class, and you get some cute examples to practice right before we open the gates of hell, which is modifications on this rule. So let me pick up, 1 or 2 quick examples to do in addition to these easy ones. So, something that you would love to hate. Let's see. Here's an amazing problem. Problem 30. They're asking you to find the limit as x goes to infinity for inverse tangent of x minus pi over 2, no coughing, divided by 1 over x. And you're looking at this and you go, why? Why? Who will ever need this, ever? And the answer is, I feel your pain. The only answer that I have to the question why is the one that my parents gave me when I was a kid, and that's because. And you just walk away. That's the answer, because. Because you can, we can, whatever. Good, let's plug in infinity. When we plug infinity for tangent x, inverse tangent x, it goes to pi over 2. You all know that because you know inverse tangent graph. We reviewed that on day 1, and I told you it's going to be there, it's going to be there in full force. So the graph, as x goes to positive infinity, right, the y value will go to pi over 2. So the whole thing is pi over 2 minus pi over 2, that's 0. And then in the denominator, 1 divided by infinity is 0. And yeah, we have 0 over 0, right? Cool. So this is 0 over 0. That means that we can unleash L'Hopital. So that's going to be limit x goes to infinity, and now we have to do some derivatives. Remember how I told you that you have to memorize inverse tangent 1? Right? Like really make sure you know it. There it is. So what is it? Very good. Nice. So derivative of the inverse tangent is 1 over 1 plus x squared. And what is the derivative of 1 over x? Very good. Great. So now what? Now we deal with the double fraction, right? So let's do some algebra before we hit this with a calculus. When you do algebra over here, two that are far apart multiply in the numerator, so that's going to be negative x squared. And the other one stays in the denominator. Do we see that this just transformed in a problem we just had? So now it's infinity over infinity. Is it? This is a really cool problem. So limit x goes to infinity, and now you take the derivative, it gets 2x on top and 2x on the bottom. And you know what, from this point I'm just going to cancel all that to -1 because I'm a boss. Yeah. The derivative of this. I'm sorry? I didn't change, I computed. I compute, and if it is 0, then I can do derivatives. If it's not 0, I can't. Right? So this is just computation to make sure that I have 0 over 0, infinity over infinity. It's just a calculation on a side. I shouldn't be even writing it, but I need to, and that's why it's red. Right? So I'm not replacing it with 0, I'm actually replacing it with this, because it's derivative. So this is what we have for our calculation over here. And you see this really cool problem, which started as 0 over 0, turned into infinity over infinity, and we were able to finish it off, right? So that's that rule. I know I promised 2 examples, but this example covered both. Or should we? Let's do one with ease. I know you love exponential functions. What are we going to do? 26, 27, 29. 26, 27, 29. 26. Sold. limit x goes to 0 of e to the x minus 1 divided by 5x squared. Go. Okay, let's take a look at the problem together. So, plug in 0. When we plug in 0, e to the 0 is 1. And then 1 minus 1 is 0. So the numerator works out to be 0. When I plug in 0 in denominator, works out to be 0. Since we have indeterminate form, 0 over 0, I am allowed, by L'Hopital's rule, so we put L apostrophe H here, to take separate derivatives of numerator and denominator, and have e to the x minus 1, and have on the bottom 10x. Now we have a new limit problem. We attempt to solve the new limit problem. Now the new limit problem you can try to plug in. We get 0 over 0 again, right? Because e to the 0 is 1, 1 minus 1 is 0. So that's that. So we can do the L'Hopital again. Don't forget to write limits. And we get e to the x over 10. And the whole thing works out to be 1 over 10, because now you plug in 0 for e and you actually get a number. And that's when the limits are done. So the entire, as I mentioned, so 4.7, L'Hopital's rule is the rule that will compute limits. So this is technically back to chapter 2, except this method is using derivatives. If you have one of the two indeterminate forms, when you try to plug value in, if you have any of those indeterminate forms, then the formula for L'Hopital kicks in, which is where you can take derivative of the numerator and derivative of the denominator independently of each other, so it's not a quotient rule, and obtain a new problem that it's completely different than the original problem, but it has the same answer. So, as I said, writing equal in between these two without L apostrophe H will trigger my allergies and fury and everything else. Because clearly they're not equal. But they have the same answer. So we still do it in some capacity. So that's the basic. The basic idea is if you have infinity over infinity or 0 divided by 0, you can use this method. Now we are going to explore other possibilities, and these other possibilities can be transformed into 0 over 0 or infinity over infinity. So whatever we're going to cover now is all going to be, you first have to do some algebra manipulation, and eventually you will get into the form of 0 over 0 or infinity, so you can do what we did so far. So these new methods are, starting with the first one, 0 times infinity case. So in order for us to do 0 times infinity case, we all have to understand a simple double fraction manipulation, which says that f of x can be written as 1 over f of x. So we need this. This will be used a lot. Now let's take a look at some examples and see in which way this plays the role. So say you have should I do these problems here? Whatever. Okay, so let's say we have the limit x goes to 0 of x times cosecant x. What you have here is 0 times infinity. When you plug in 0 for this, you get 0. When you plug in into cosecant, you get 0. No, you get infinity, sorry. Cosecant, if you don't remember, is a flip of sign. So it looks like this. It's a U shape over here and a U shape on the bottom. And the sign is just there to construct. So you can see that as x goes to infinity, right, from this side, it shoots to positive infinity on top. So as it goes to 0, right, because limit goes to 0, as the limit goes to 0, you see that the y value goes to infinity. So we have 0 times infinity, and then this is this new case, which we have to study. So now, which way do I do this? Well, I write one of the functions using this. So let's use that on the cosecant and see if we can solve the problem quickly that way. If it doesn't work, you just backtrack and change the other one, see if that works. So I'm going to leave x as is, and I'm going to apply the formula. So this is now equal to 1 over cosecant x. So I use this on the cosecant, right? So the next step is the limit x goes to 0 of x times, and now 1 over cosecant x is 1 over sine x. So what do I have? Well, what I have is the limit of x over sine x. Now we already know what this is. What is it? 1. But the most important part here is that we actually got to the place where you have 0 over 0. You see, we use the transformation of 1 over f. We use the transformation to change it from 0 times infinity into, in this case, 0 over 0. So now we can do the L'Hopital. We get limit x goes to 0 of 1 over cosine x, which is 1 over 1, which is 1, just like in our previous example. So what are we using? We are using the fact that f of x is equal to 1 over f of x. So that's just a algebra 1 manipulation, right? That you would do in algebra 1 with fractions or whatever. Now we just put the function in there instead of number, and there you go. Let's find another example. You hear this as well, right? Okay. No, just wanted to make sure, you know, because when voices start talking. Oh, you should never be confident. It's not the issue that they talk, it's the issue of what they say. Yeah. Right? Yeah, who cares? All right. There's a real shortage of these examples in the textbook, unfortunately, so... Oh, we can do this one. Limit x approaching pi over 2 from the left of x minus pi over 2 times the tangent of x. These examples, they will have trig. They don't need to have trig, but okay, fine. There you go. So now when you plug stuff in, clearly the first parenthesis pi over 2 minus pi over 2, and that's a 0. And the tangent, right, whose graph goes like that, when you approach pi over 2 from the left, you get positive infinity. So we have 0 times infinity deal, and we can use our trick f equals 1 over f to go through this. So let me write the limit. X goes to pi over 2 from the left. And now I'm going to put x minus pi over 2 divided by 1 over tangent x. So this tangent x was in the numerator. Now it goes in the denominator as 1 over tangent. And what's 1 over tangent? What?
Cotangent.
Cotangent. Thank you very much for being attentive. Well, no, you are succeeding, actually. So, do or do not. There is no try. There we go. The rest of you. Actually, I shouldn't do that. I should do this. You understand that. If I do it, you might not know what it means, but if I put that, then it's like, yeah, okay, we got it, sure. Okay, so cotangent now cotangent graph is actually shifted, and it goes through pi over 2. So now when you try pi over 2, you get 0 over 0. Emotion, please? No? Thank you. Well, okay, fine. I'll give you no emotion here. But the next one, I think you just gotta do it of your own accord. So now we have 0 over 0, which means that we can do our derivatives, right? And if we do our derivatives, I will have limit x goes to pi over 2 from the left. The numerator has the derivative of x is 1. Derivative of pi over 2 is 0. And derivative of cotangent is negative cosecant squared x. Thank you very much. What's the cosecant of pi over 2? It's getting worse. So to calculate cosecant, you calculate sine. And then cosecant is 1 over whatever you get for sine. Because the cosecant theta is 1 over sine theta. So if I have to compute cosecant at pi over 2, I am actually computing sine of pi over 2. So that's 1 over 1. So it's 1. And then you square it and make it negative, so the whole thing is just negative 1. And then you had that negative in front, so yeah. Maybe I should put in an extra step. 1 divided by negative 1 equals negative 1. There we go. Now we have all the steps. So that's the procedure for 0 times infinity. There's nothing else to it. You will have to change either the first function or the second function. If you change the wrong function, you will know, because derivatives will make it worse. See, if I was to change this, the previous one was, I think, over x or something like that. If I change that to 1 over x, then the derivative of 1 over x is negative 1 over x squared. And then the derivative of that, if you want to go with another L'Hopital, is going to be x, 1 over x cubed, and so on. And it's going to get worse over time. So if you keep doing L'Hopital and the expression is getting worse, well, you flipped the wrong function. So go back from scratch and flip the other one. So I tried. I have immense experience, and I just know everything. But I tried with the cosecant because I like flipping the trig functions, because trig functions are contained, and then I'm not changing the input, but by changing this trig function here, I'm changing that input, moving it from zeros into ones and ones into zeros and so on, right? So it's good to try and flip the trig function first. It's not guaranteed that it's always going to work. So if it makes it worse, you go back and you flip the other. I should say, let's start the new notebook, but we can maybe contain it on a new page. We'll see. Infinity minus infinity. What was the goal? Goal is to get 0 over 0 or infinity over infinity. Right? That's the goal. I have subtraction. How do you go from subtraction into division?
Expansion of like a log, using the expansion of numbers.
It is a thing, but unfortunately we can't add logs in between the right minus sign. We can log the whole thing, but then it's log of subtraction. That's not a rule. There was an amazing attempt to do this, but no, really, no one ever. Oh, what do we have? So we have to go from subtraction to division. The only way that you can make that journey is to go from subtraction into multiplication by factoring, and then go from there to division by 1 over f. You see that transformation? So we have to factor to make it multiplication, and then use the trick from the previous stuff to go into division, and then we can finally do L'Hopital's rule. So let's go. How about we go green on this one? Path goes subtraction, goes into multiplication, goes into division. Now over here we do it by factoring, and over here we do it by 1 over f. It's a very convoluted, right? Let's take a look at the example. Start a new page. So it's a procedure, guys. There's no formula. It's just a procedure. Evaluate the limit as x goes to infinity of x minus the square root of x squared minus 3x. Yeah, I know. Why? Grow up. What would your intuition tell you? What is infinity minus infinity? Is it just 0? Or is it? Like, shouldn't each one of these be 0 if you subtract infinity from infinity and be done, right? And the answer is no. It could be 0, it could be infinity, or it could be half, or 3/4, or whatever. You will have to compute. And the most interesting part here, for me at least as a student, was that you subtract infinity minus infinity, and sometimes you get 0, sometimes you get quarter, sometimes you get infinity. And that will depend on the type and growth and everything else of these functions that you are subtracting. But that's slowly moving into advanced calculus analysis and things like that. So we don't have to worry. We're just going to compute here. What am I supposed to do? I'm supposed to factor so that I can change subtraction into multiplication. Well, it should be obvious that the thing that I'm factoring is x, which means that I need an x over there, and I don't have it. So since I don't have the x that goes here, I need to make it, and to get an x there, I have to be able to factor x squared from here. But then this one doesn't have x squared. And that's as deep as this rabbit hole goes. There are problems with the deeper rabbit hole, but right? So this is the process of thinking that you need to employ all the way back to get the first step completed. So you go over here and say, okay, I am factoring x. In order to factor x from two terms, I have to have an x. The only way to get x in front of the square root is to get x squared factored here, and then that x squared jumps out as a single x. But now I have to have two x squareds that I can factor here, so it can jump out. I have x squared here, but I don't have one here. So you see that everything kind of punches on me fixing this term. When I make this into x squared, I'll have x squared to factor. That x squared will be x here, and then I can factor x, and then I have my multiplication. And then we do the rest of the problem. Right. Okay. So my job with all of this backwards thinking, my job is to make this into 3x squared somehow. And that's obtained very easy by multiplying top and bottom by x. That's that. And there's your 3x squared. Well, I just need x squared. So as soon as I do that, limit x goes to infinity, x minus square root of x squared minus 3x squared over x. Limit x goes to infinity, x minus square root of x squared times 1 minus 3 over x, when I take x squared common factor. Now this x squared is going to jump out, and we are going to have x minus x square root of 1 minus 3 over x. And finally, limit x goes to infinity, you factor out x, and you are left with 1 minus the square root of 1 minus 3 over x. first step completed. So what do I have now? Well, I have infinity times 0, which means 1 over f to change it into 0 over 0 or infinity over infinity, right? So we are about, I don't know, a third way in of the problem or halfway, whatever. We have to, now, we realize that this is infinity times 0. Right, what's 3 over infinity? 3 over infinity is 0. So square root of 1 is 1, 1 minus 1 is 0. So now when we have 0 times infinity, this is where I go and say, use f equals 1 over f. Limit x goes to infinity. 1 minus square root of 1 minus 3 over x divided by 1 over x. Testing. 1, 2, 3, 1, 2, 3. Plug in infinity. And we have 0 over 0. We can finally start doing the problem, right? So what you've seen so far is a prep to transform infinity minus infinity into 0 over 0 or infinity over infinity, whatever you get once you're done with all the transformations. So we did a whole bunch of factoring, and then eventually the function flip at the end to get to this point. And now it's derivative time, right? So this is equal by L'Hopital to the limit x goes to infinity, negative 1 over x squared in the denominator. That's given. Now the derivative of numerator. Is anyone looking forward to it? Thank you. Derivative of 1 is 0. So we copy the negative. And now we have a square root, which is parentheses to the 1/2, right? So technically we are taking the derivative of 1 minus 3 over x to the negative 1/2. Sorry, to the positive 1/2. So what do you have? You have a 1/2, 1 minus 3 to the x to the negative 1/2, times the derivative of the inside, and the derivative of the inside is negative 3 over x squared. You know that the derivative of 1 over x is negative 1 over x squared. Well, the derivative of 3 over x is negative 3 over x squared. And then you have to be careful with signs. It's a plus, because you have a minus over here, so that's a negative 3. So that minus, and then you have also, when you take the derivative of just 1 over x, you get negative 1 over x squared. So that minus from that calculation and this minus from here together make a plus over there. All right, so what do I have? I have a negative cancel a negative, and I have x squared denominator cancel x squared denominator, and I lose denominator altogether, at least in this capacity here. So let's see what we get now. What survived? Well, 3/2 definitely survived. And the whole thing over here is 1 over the square root of 1 minus 3 over x. Because it's a negative 1/2, that means the negative means it has to be shipped downstairs. And then you have the square root for 1/2. So now plug in. When you plug in infinity, right? Three over x goes to 0. and you have 1 divided by 1 is 1, so just 3/2 survives in front. So next time someone tells you, what do you know? Or tell you stupid or something, you just say, I can subtract 2 infinities, get 3/2. Right? Who knew? Infinity minus infinity equal 3/2. Now, if you trace this number 3 through the problem, you see how I can make this problem to be any value I want, right? I keep changing this 3 into whatever value I want, and I can make the answer for this limit to be anything. So yeah, that's that cool part. Should we do another one of these subtraction ones? These are the longest and the most painful of all. Ooh. Let's go with tangent minus secant, because we can. Limit theta goes to pi over 2 from the left, and it's tangent theta minus secant theta. No. Well, it's infinity minus infinity. Both of these guys have a vertical asymptote at pi over 2, because both of these guys have cosine in the denominator, right? So cosine is 0 at pi over 2, so it's a vertical asymptote there. Great. Perfect. When we have infinity minus infinity, we know that the first order of business is to factor whatever is common to make it into multiplication. What's common? Cosine is common. Now you would go, but I don't see any cosine. I'll write it so you can see it. So sine theta over cosine theta minus 1 over cosine theta. And this is where your factoring comes in. So limit theta goes to pi over 2 inverse. It's from the left, sorry, not inverse. And then you are factoring 1 over cosine theta, and you are left with sine theta minus 1. I hope you see that this is now infinity times 0. Because cosine of pi over 2 is 0. 1 divided by 0 is infinity. And sine of pi over 2 is 1. 1 minus 1 is 0. So infinity times 0. Now I need to flip. Theta goes to pi over 2 from the left. On top I have a sine theta minus 1. Denominator in this case is confusing because it's 1 over cosine theta. Because this thing is 1 over cosine theta. It's not x. If it was just x, then it goes denominator 1 over x. But this is like 1 over x, which means 1 over x. Math fun. So you have to be careful about that. Now, good thing is that we know that 1 over cosine is secant, and then 1 over secant is cosine for the whole denominator, just cosine. So we have sine theta minus 1 over cosine theta. Again, 1 over cosine is secant, and then 1 over secant is cosine, so it just flips twice. Plug in pi over 2, what's happening? We have 1 minus 1, so it's 0 over 0. That's the yay moment, because we have division, and it turned out to be improper indeterminate form, which means we get to use the L'Hopital's rule. The limit theta goes to pi over 2 from the left. The derivative in the numerator is cosine theta. The derivative in the denominator is minus sine theta. For the total of cotangent theta, as theta goes to pi over 2. And cotangent theta at pi over 2 is very good. Yeah, it is. Details, yep. Here, I'll put negative 1 in front. Negative 1 times 0, 0. Yeah, it is negative. So, in my opinion, these are the scariest ones, minus and minus. If you learn the procedure, subtraction by factoring into multiplication, and then multiplication by the trick into division, you're okay. And let's say you know that, but then I hit you with what's common. Do you all know that cosines are common? Right? So if you have trig, if you are getting stuck, expand all those non-sine and non-cosine functions into sine and cosine based functions, so that you can identities, so that you can progress. You have to have something in common in order for it to be factored and changed into multiplication, and then use the trick to go from multiplication into division. Second to last part of the lecture, which is the part 4. We had the basic one, we had the multiplication, we had the subtraction. Now we're going to have all the exponential ones. And then the part 5 is learning about the growth rate of functions. So now, what are we dealing with? We are dealing with 1 to infinity, 0 to 0, and infinity raised to 0. So how much is 1 raised to infinity? Well, what does it mean, exponents, right there? So it means multiply 1 infinitely many times. And what should that amount to? Common sense tells us 1. But no. Right? Common sense tells us 1. And we all have to sign off on that. Because 1 times 1 times 1 times 1 times 1, right? So, yeah, I thought the same thing. Now, let's take a look even more interesting over here. Look at this puppy. What's a 0 raised to anything? 0. And what's anything raised to 0? 1. And this thing is on the paper, so they can't take it outside. It has to be resolved right here. So, is it going to be 0 or is it going to be 1? Right? Which one? And again, it depends on the problem. So we are going to solve this and get 10. And we're going to solve this and get 0, 1, or 3/4. Same here. Right? Infinity raised to anything. That's infinity times infinity times infinity times infinity. And then I come up with 3/4 at the end. And you go, what? Infinity raised to 0 3/4? Really? So, what I'm asking you in short, retire your common sense here, please. Retire it completely And then if you take Calc 2 with me, I will be asking you to retire your common sense again when we are in Chapter 8. So let's solve these problems. And how do we turn exponents into multiplication now? Oh, it's passed out. So how do we change the exponents into... I needed him to give me the same answer because that's the answer. Log, exactly, ln, right? That's how I solve it. Hey! It's log, of course, it's always log. Nice. So let's take a look at the wonderful example of, let's say, limit of x raised to the 2x as x goes to 0 plus. From the right. So you're looking at this monstrosity and you immediately conclude that this is 0 to 0, right? Because you plug in the zeros for x's and what you have is 0 raised to the 0. Fine. Your job is to change this into multiplication and then you will do the 1 over 1 over f to get it into indeterminate form. And then you will use the derivatives to solve the problem. We start by saying y equals limit x to the 2x. And then we are going to ln both sides. And when I do that, I have ln y is equal to, I will kick the limit all the way out. And finally, I have 2x ln x. The exponent of 2x that was on the argument is kicked outside. You have to remember the formula. Ln x to the p is p ln x. That's what we are using. Bueno? Sí. Okay. So now, look at that. It's 0 times negative infinity, right? Because ln of 0 is negative infinity. If you know your ln graph, it's obvious. As you are going towards 0, you go to negative infinity. So the whole thing, I don't know why I erased the graph. Graph's good. So the whole thing over here is 0 times negative infinity, which is 0 times infinity. And we know that we have to flip one of these guys. So ln y is equal to the limit. X goes to 0. And then I have 2x. Sorry, I'll leave ln x. And on the bottom, I have 1 over 2x. You know what? I'm going to leave this 2 with ln. You know what? I'm going to kick... Nah. I was about to kick it in front of the limit, but then you might not find it. So let's keep it there. What do I have? I have infinity over infinity now. Ln of x, as x goes to 0, is negative infinity. And 1 over 0 is infinity. So we have infinity, infinity. Nice. So now we can hit this with derivatives. But don't forget to put L'Hopital on the equal. The derivative on top is 2 over x. The derivative of the bottom is negative 1 over x squared. This further is the limit of x going to 0, right? And then you put x squared, so we'll cancel. So it's, right, negative 2x, which is 0. So this is our So negative 2x, and that's that. So now we have negative 2 times 0 is 0, and we see that in this particular case, our 0 to the 0 gives us 0 at the end. Again, with different functions, different results. Let's do another example of this. This looks bad enough. 62. Limit as x goes to 0 of e to the 5x plus x raised to 1 over x. Excited? No? Saturday. It's close. Plug in 0. When you plug in 0, this guy is 1, plus this guy is 0. All of that raised to infinity. Yay! It's 1 to infinity. So e to the 0 is 1, plus 0 is 1, and 1 over 0 is infinity, so 1 to infinity. Good. Y equals limit x goes to 0 of e to the 5x plus x to the exponent of 1 over x. And then we have ln both sides. Ln y is equal to kick the limit outside, put the power in front of ln, and that's that. Now what? What now? Well, we should check first, because if it's 0 times 0 or infinity times infinity, it's the wrong method to solve the problem, right? So we first have to check. In the first one, when you plug in x equals 0, what do you get? Infinity. And in the second one, as you plug in 0, you get 0 because it's ln of 1. This thing goes to 1 plus this thing is 0. So you get 1 plus 0 is 1. Ln of 1 is 0. So that's 0. So now we can go, as you said, under. So ln of e to the 5x plus x divided by hold on. Oh, I forgot the limit, that's why. Limit x goes to 0. So this stays as is over here. Oh, I forgot the L'Hopital. I lost 2 points over there. So you have 1 over x. I know, right? It's woohoo! Your formula is 1 over, right? So that's 1 over from the formula, the big one. And then this should be 1 over f. but your f is 1 over x. So clearly it's going to be a string forever. Right? If your f is 1 over x, then this is your f. So you only have 1 over f. So the whole thing is 1 over f. But your f is 1 over x, so it towers down. Which is just equal to x. Isn't that the flip of a flip is right side up? Flip of a flip is the right side up. No one? When you flip your sweater and you flip it again, you get the right side up. So, I flip the flip. When I flip the flip, I get the right side up. Let's check. The top is 0, the bottom is 0. Yay! So now we can do our limits. Oh wait, this is not L'Hopital. This is next one is L'Hopital. This is just manipulation. Here is L'Hopital. We take derivatives. That was a wrong spot to put that. Denominator is 1. What's the derivative of the numerator? It's ln, so it's easy. You just copy the function as is. And then put its derivative upstairs. So all I need to do is to compute 0 in this, and 0 computed in this is a joke. So ln of y is L apostrophe h. Oh, no, I don't need a limit anymore. So now look, L apostrophe h is, we have 5 times 1 plus 1 divided by 1, because e to the 0 is 1, plus 0. So the whole thing is 6. ln y is equal to 6. If ln y is equal to 6, then y alone is e to the 6. But y was the original problem. Oh, I haven't done that.
Yeah.
Holy nightmare. We have to go back and fix that. The answer is not 0. The answer is 1. Because we have that ln y is equal to 0. So y is equal to e to the 0, which is 1. So the limit is 1. Holy nightmare. Alright. So let's fix this first. So now what I have here is that the procedure gives me 6. I'm realizing that's not the y equals. So I have to deal with that. So y is equal to this. Now y was defined to be limit as x goes to 0 of e to the 5x plus x raised to 1 over x, and that is equal to e to the 6. So this was 1 to infinity problem, and the answer was finite, e to the 6. Now going back to the previous example, my y was x to the x squared, so the answer is that the limit x goes to 0 of x to the 2x is equal to 1. That's the answer. Alright, copy that first. So ln y is equal to 0, and now you have to fish out what y is on its own. So you e both sides and you get y on its own. And yeah. The only thing that is left in this section is growth rate of functions. We talked about running earlier, and we are really familiar with the concept of some people being faster than others. So when you watch a race, someone is going to win, and someone is going to be in the last place. Still has his trophy, but it's in the last place. Right? So, yeah. So this is going to be that thing. We are going to have functions for which when you plug in a value are going to grow faster than others. You see, you can have a function x, and x is just going to count 1, 2, 3, 4. It grows. 4 is bigger than 3, 3 is bigger than 2, 2 is bigger than 1. So you go 1, 2, 3, 4, 5, 6, 7, right? It grows. It's a linear growth. I can make that linear growth faster by, let's say, 3x plus 1, right? So that grows faster. But I can also make it faster if I put it x squared, because x grows 1, 2, 3, 4, 5. X squared goes 1, 4, 9, 16, 25, right? Much bigger. So we want to line up these functions in categories, right? And say, you know what? Logs, the sluggish, slow. And then square roots. And then polynomials. Whether it's a linear polynomial or x to 100, they all go in the same bag and they are third. Then the next one, when you multiply polynomial with the ln, the product of the two should grow faster than the individual ones. So that's the next step in evolution. But then we say we have exponential growth, right? Technically, the problem we did earlier, x to the x, that one is the boss, all right? That's the fastest growth. We can make it faster, sure, right? Because you can just put x to the x squared, and that's going to go faster, right? But it's of that form. So I'm talking about form, right? So let's take a look at these groups. I think they're using P's and Q's and LNs. Okay, so growth rate. As x goes to infinity. Guys, you are going to use this and expand in Calc 2. If you're going to Calc 2, this section is absolutely a must. Half of your Calc 2 is integrals and half of your Calc 2 is limits. And there will be derivative here and there, occasionally. You know, every other month. But limits, and that's Calc 2. So, growth rate. ln raised to any power of x is slower than x to the p, which is the polynomials, is slower than the multiplication of the 2, which is x to the p ln q, is slower than multiplication of 2 polynomials, let's say p plus s, is slower than exponential function, is slower than the boss, x to the x. And you can quickly see this in a table of values. If you go x, 2x, x squared, 2 to the x, and x to the x, and you populate this for 1, 2, 3, 4, 5, 6, when you compute the numbers, you will see that these first 3 guys, they're all polynomials. They don't grow as fast. So 2, 4, 6, 8, 10, 12. Then we have a squares. That's 1, 4, 9, 16, 25, 36. Then we have exponents. Right? 2 to the 1 is, so 2, 4, 8, 16, 32, 64. And it really has to be evident in the last line that you are at the same level, but you are getting bigger values, which is the faster growth. And then x to the x, 1 to the 1 is 1, 2 squared is 4, and then 3 cubed is 27, and then 4 to the 4, 4 to the 4? 256, because it's 16 squared. You see that? And now you have 5 to the 5. Yeah, it's a lot. It's 3,000 something. 3,000 something 25. Okay, that's what it is. I'll give you the first and the last two digits, and then there is a digit in here. 125. Okay, great. Look at that growth. Now 6 to the 6. That's 6 to the 6 is really large value. Let's see. So 6 to the 6, what do we get?
46,656.
Thank you. You see why I call it the boss? Right? The rest are still playing in sand. Look at this one. Right? So that's the growth rate of functions. Now, why do we want to do this? I sneaked it in here. I didn't talk about it. Technically, this is not mathematical notation, and you haven't seen it here, okay? Not that it's live streamed or anything, but the limit as x goes to infinity of slow over fast is going to be 0. And the limit x goes to infinity of fast over slow is infinity. And that should be common sense, right? X over x squared is going to be 0. X squared over x is infinity. So this will also help a great deal if you are dealing with the functions that are not of the same type. Like, you can deal with asymptotes, for instance. You have polynomial divide by polynomial, and you learn the Q rules, or you do the divide by highest exponent. Well, what you're going to do if it's e to the x combined with the polynomial? You do this one. Because polynomial is slow, e to the x is fast. It depends which one is on top. Right? And that's that. So I'll take a few minutes to breathe. When we come back, integration. It's going to be fun.